Proofs are mathematicians' ways of explaining and justifying why some argument or finding is true in writing. It is done by using axioms, using previous proofs, and fundamental mathematical definitions. We use it to learn more from what we already know and what has been proved before, and it's used to help convince other mathematicians that something is true, some finding is true, and help them to learn why it is true.
Go ahead.
So today I'm going to be talking about how we write proofs and how to prove something. So generally we start with something that we know to be true, some universal mathematical truth or some given, and then we use a common technique such as induction, proof by contradiction, direct proof, proof by cases, proof by contrapositive, and we use these two things together to reach our final conclusion, which we hope to prove to be true or we can show to be false. For problem number 5, what we started with was the idea that if two sets have the same cardinality, there is a bijection between them, which is a proven theorem. And so how we did that was we tried to show a bijection between the set of infinite sequences of integers and the natural numbers, which we know is denumerable, so therefore countably infinite. And so if we're going to show that this set is countably infinite, we could make a bijection between the natural numbers in this set. So the first way we tried to do that was just by counting. So we used the same way that we showed that the integers are countable with this set. We started with the infinite sequence of all zeros, and then infinite sequence of all zeros with a 1, negative 1, and you can complete this as many times as natural numbers exist. And so we said some arbitrarily large natural number L would map to the infinite sequence of all zeros, and then some P, which is an element of Z, and then naturally L plus 1 would map to the same sequence with a negative P. But at some point you have to move on to moving over an index. And since L is arbitrarily large, we said this would be at L plus 2. And so we go 0, 0, infinite number of zeros, 1, 0. However, you can show that the contradiction exists because all you have to do is add 1 to P, and there's no natural number between L plus 1 and L plus 2 that maps to that element of our set, which is therefore not a bijection. So then we use something else we've seen before, a common technique to show that something is countable is by showing a table like this. We did the same thing with the set of rational numbers. And if you can draw a line or a diagonal or something of finite length, and if you do it infinitely many times, you can show that you take an infinite number of finite steps that will get you eventually to an answer. And so we showed this with tuples of 2. So for example, 0, 0, 0, 1, 1, 0. We use this table and we showed that we can make finite steps. In this case, this diagonal is 1 and they sum to 0. This diagonal contains 2 tuples, which both sum to 1, 3 tuples, which sum to 2. So we tried to extend this idea out to infinity, infinite number of dimensions. And so we sought to create a bijection between the natural numbers and infinite sequence, the set of infinite sequences of integers. And so we started at a natural starting place, which is all zeros, because these all sum, the elements of this sequence all sum to 0. And we tried to find the elements, all the sequences whose elements sum to 1. And so naturally we thought that would be infinite zeros with a 1 at each index. And so there's all these. But then quickly another contradiction arose. And the idea was that you could add 1 here and subtract 1 here, and then that would still sum to 1. And you could do that uncountably infinite number of times. There's no limit to how many times you can do that. And so therefore there would be an uncountably infinite number of these sequences, meaning the set is not denumerable. And so after we found specifically these 2 contradictions trying to prove this theorem this conjecture to be true, we determined that this conjecture is probably false, and we sought to disprove it.
We're attempting to prove that the set of infinite sequences of integers is uncountable. To do this, we're going to use a proof by contradiction. So we start by assuming that the set S of infinite sequences of integers is in fact countable. And from that, we can conclude that since the set's infinite, it must be denumerable. And then, therefore, there exists a bijection from the natural numbers to S. So we define our bijection F for each element of the natural numbers so that we have an output that's a sequence where each element of the sequence is denoted by a small a with a subscript that describes its position in the sequence as well as its the natural number that it's the image of. So for example, for f of 2, we have a sub 2, 2, which means that it is in the image of the natural number 2, and that it's in the second position in that sequence. So we're going to show that f is not on 2 by defining a new sequence, s sub b, which is going to contain elements b1, b2, b3, and so on. And each b is going to be either a 4 or a 5. And this is going to allow us to generate a new sequence that's not covered under any of these sequences that are images from our bijection. So basically what we have is if an element at, say, the 1, 1 position in f of 1 is a 5, then b1 will be a 4. And if that element is not a 5, then the corresponding b for that position will be a 5. So what we're doing is we're taking, making a new sequence where we say, so we have our A11, and we're going to choose a different value for our new sequence. A22, choose a different value. A33, choose a different value. And we're continuing on through all of the natural numbers. And what that's going to do is give us a new sequence, S sub b, that has at least one distinct element from every sequence generated by our bijection, and therefore it's not an image of any natural number under our bijection f. This means that our function is not on 2, and therefore cannot be bijective. This contradicts our original assumption that if the set S was countable, then we could find a bijection from the natural numbers to the set S, and therefore we conclude that S is uncountable.